There goes. Okay, part 2 of our practice test. We have two equal but opposite point charges located near each other. Position A is midway between the two charges, and position X is directly above position A. Two students are discussing how much work would it take to go from position X to position A. Let's look at student 1. Since electric potential depends on the reciprocal of the distance to the charge, as a proton moves closer to A, the electric potential will increase, causing the need for work to be done on the proton. Here's a graph of potential versus distance, and we'll see what that looks like. Okay, so that person drew voltage increasing because we're getting closer, and of course it's a curvature based on 1 over r. Alright, next, student 2. I agree that electric potential depends on the reciprocal of the distance to the charge, but you've forgotten that there is a negative charge. Since we are approaching the negative charge as well, the electric potential would decrease, causing the amount of work to start with a larger value, but it'll gradually decrease. Here is my graph of what it looks like. Same kind of graph, except going the opposite direction. Let's evaluate each student now. Okay, we agree that electric potential does depend on 1 over r. Disagree, there is no increase in potential using superposition principle. The sum of the potential between negative Q and Q is always equal to 0. Critique the ideas of student 2. Yes, still agree that 1 over r is what electric potential depends on, but as previously stated, there is no potential. What would the graph look like? Pretty much a flat line at 0, and no work will be done, okay, to move that charge there, since the potential is 0 the entire time. Alright, now that's that question there. We're going to move on to further questions of review. Alright, now we're looking at still more review for the electrostatics test. Here goes. Let's take a look. So electron source, which is right here, fires electrons to these holes. We see that there is an increase in velocity, I believe from 5.4 times 10 to the 6 to 8.02 times 10 to the 6 meters per second, taking 1.49 nanoseconds to do that. So we need to figure out which one's positive and which one's negative. Okay, the top plate's got to be negative, positive one's got to be in the bottom, because if I'm an electron, I go against the electric field as I go from a negative to a positive charge. So that would make sense because they're accelerating in that direction. Calculate the magnitude of the electric field between the plates. Well, I believe I went through force this time. You can do a variety of things. So I got the, we know, okay, that velocity final must equal velocity initial plus AT. It's just a regular kinematic equation. So I got my two velocities. I divide. There's my acceleration, 1.8 times 10 to the 15th roughly. I'm now doing mass times acceleration for the electron to get my force electric, and then I divide it by the charge of an electron and get about 10,000 newtons per coulomb of electric field. Okay, calculate the charge on each of the plates. You do not have to do this part of the question. This is the next chapter. We can definitely do the change in electric potential energy, okay, for these between the plates. Because if we know the voltage, okay, voltage is equal to E times D from question 4. Here's my volts, there's the distance between my plate. All I gotta do is take that 110 voltage difference between the plates and multiply it by the charge of an electron and get 1.8 times 10 to the minus 17 joules. Okay, so electric field. Now the distance between the plates should have been revealed up here in my caption. There's the distance right there. There we go. Alright, the next question, figure 2. A positively charged sphere is on a light string, which means you don't have to worry about the mass of it, and is pushed to an angle theta due to the electric field between the plate. Okay, let's determine which plate is positive, which is negative. So this is a positively charged sphere. It's being pushed this way, therefore the plus charge has to be here and the minus charge is here. And of course there are parallel lines, okay, that are between the plates. That's electric field lines. Okay, derive an equation in order to determine the value of the charge on the sphere in terms of electric field and angle theta, the mass of the sphere, and any universal constants. Okay, a little bit trickier question here. So what I did is I did draw a free body diagram here. Okay, here is our cable going this way. We of course have gravity downwards, force tension Y upwards, and of course those two are going to equal each other. If this is our angle theta here, it's also here. So this is a common thing that we have seen. So we know that these two must be equal to each other. Force tension Y is actually equal to mg. What's force tension Y equal to? Force tension times cosine of theta, since our angle theta is there. And we get force tension equals mg divided by cosine theta. Now force tension X is pointing this way. That's going to be completely opposed by force electric going against it. So this ball wants to fall downwards, but force electric is pushing it away. So then we know that force tension X must equal the force of gravity. Okay. Alright, so force tension X must equal force electric, excuse me. So what do I do there? Okay, I'm going to put force tension in here. Okay, I'm going to multiply that by the sine of theta to get equal force electric. Force electric equals mg tangent of theta. Okay. Now I know what my force electric is equal to. I can then figure out what my charge is equal to. Okay, how is that possible? Well, I know that force electric is also equal to EQ. So I know my force electric is mg tan theta. I place that here. I'm multiplying my force electric. I'm converting into E times Q. Solving for Q, I'm going to divide that to the other side. So again, you got to remember that force electric does equal electric field times the charge value. Next, explain any changes in figure 2 that would occur if the metal plates were moved closer together. Well, electric field will increase as the plates move closer together. The charge of Q doesn't change, so the angle theta has to get larger. Okay, so if E gets bigger, theta's got to get larger in order to keep Q the same. And that kind of makes sense. Basically what you're getting is a greater push on that charge to go to the right. Now assume that the distance between the plates is 5.6 centimeters. What is the potential difference required between the plates to keep a 5.2 gram sphere with a charge of 17.3 microcoulombs at an angle of 25 degrees? Well, we're going to place values in and actually solve for electric field here. We're placing it into mg times theta divided by Q. And you get electric field value of 1,370 newtons per coulomb. Using the volts equals ED equation, you can figure out your volts. So there's our volts multiplied by the distance between the plates. Okay, let's continue. Okay. And what we've got now is a AP style question. And I will continue that with my next video. You want to play